Hello, I'm Roddy Collins, and on behalf of my co-authors, I'll be presenting Kitware's paper From Leaderboard to Operations, DIVA Transition Experiences. Kitware is a member of the IARPA DIVA program's test and evaluation team. Our paper describes our work to transition the systems developed by DIVA performers from the program's evaluation framework to environments that are more operationally oriented. We'll briefly review the DIVA program goals. We'll examine the evaluation framework DIVA performers coded against and how that compares against operational needs. We'll describe some of the challenges we encountered and solutions we developed, particularly focusing on the issue of delivering systems that transition partners can train for new activities. We'll discuss some details of our transition activities, in particular the use of AWS, working with OpenMPF, and adapting our open source visualization tools for the DIVA systems. And finally, we'll review some lessons learned on the effort and how these might be applied to future programs. The IARPA Deep Intermodal Video Analytics, or DIVA program, is a 4-year effort sponsoring research and development of algorithms for recognizing activities in public safety style video. Teams from academia and industry produce systems capable of processing in real time multiple streams of 1080p video. Teams were evaluated by NIST on data collected and annotated by Kitware. On the left are sample video and ground truth publicly available at mivadata.org. On the right is a screenshot of NIST's Activities in Extended Video, or ACTIV, leaderboard, available at active.nist.gov. In order to support efficiently evaluating multiple submissions on hundreds of hours of video, NIST designed an Evaluation Command Line Interface, or CLI. All DIVA and ACTIV systems support the CLI, which features several design choices that must be addressed during transition. Performers have wide latitude in implementing their system. In particular, the use of container technology such as Docker is not required. In order to minimize overhead and processing time lost due to system errors, the CLI is oriented around so-called chunks, or sets of videos which are processed as a unit. To maintain the security of the sequestered evaluation, systems cannot access the internet once processing begins. And the system output is optimized for NIST scoring algorithms and software. These design decisions, while entirely appropriate for robust evaluation of multiple research systems on hundreds of hours of video, require adjustment when preparing individual systems for transition partners for assessment. From a transition perspective, the challenges we faced and solutions we developed included installation. The CLI reinstalls the system each time, including various software dependencies. NIST supplied a so-called few-shot script to isolate system and dependency installation actions to allow one-time installation and to identify areas where elevated system privileges were required. Since 2019, the DIVA program data has been focused on a single set of evaluation data, with only one change to the associated encoding parameters. Since these parameters are not guaranteed to be those used by potential transition partners, we developed an evaluation suite of video clips with many encoding variations to identify where system robustness could be improved. The DIVA program has also focused on the 37 publicly known DIVA activities, with additional efforts spent supporting a surprise activity protocol to address few-shot learning. To address this, we've been working with partners to annotate and train DIVA systems on novel activities occurring in partner data. Across all these challenges, we have also been working to identify and fix low-level software issues, such as hard-coded path names and fixed-size data structures. The DIVA program recognizes that systems must be extensible to be useful. The baseline capabilities are the 37 known activities, initially developed using data from a known facility, where video data and metadata such as camera models are provided to the performers. For DIVA, this known facility data is the MIVA dataset. Extensibility is measured in both the data domain via the unknown facility dataset, whose video is withheld from performers, and in the activity domain. For a controlled, repeatable evaluation, this is accomplished via the surprise activity protocol, in which at evaluation time after network access is disabled, the system is provided up to 10 annotated video exemplars of a surprise activity along with a brief text description. This exercises the few-shot learning capability of the system. In an operational environment, transition partners must be able to train a system for new activities without the active involvement of the developers. This process starts with the performers documenting their training procedure. We've followed their documentation at our facility on a shared set of data and annotations and compared the results we obtained with those obtained by the performers using NIST's active scoring protocol. We then used the training protocol on test videos not available to the performer, some of which were not annotated and could only be qualitatively assessed. This provided some measure of the system's extensibility. Together, these steps verified that the system's documentation for training a system for new activities was correct. As well as working to decouple systems from the DIVA evaluation infrastructure, we explored potential next steps for how DIVA systems could be used. These included using Amazon EC2 instances as both a portability test and an execution resource for system testing and verification. OpenMPF is a popular open source framework for media analytics, with a set of APIs to integrate systems via fundamental computer vision data types, such as detections and tracks. We developed a proof of concept adaptation of a DIVA system as a component in an OpenMPF pipeline. We also use DIVA requirements to extend DIVE, Kitware's open source video annotation and analytics platform, into a system capable of viewing DIVA video, annotations, and outputs. The DIVE tool natively displays video in either a web browser or a cross-platform standalone client. Video can be played, scrolled, zoomed, and panned. Detections are displayed directly on the video, as well as on a timeline in the lower part of the display. The user can filter detections by confidence level using the slider or by type using the type filter. We've made visualizations of the MIVA data ground truth available via the DIVE web app hosted at viami.kitware.com. If you visit mivadata.org, you'll see a link which leads to viami.kitware.com. After creating an account, you can click here to view the available clips. Click Launch Annotator to launch DIVE. Our experiences helping potential partners assess DIVA systems have yielded some insights into future areas for work. These include the assumption that target systems can easily meet the software dependency checks required by DIVA. We have observed many corner cases in partner video data, which we have incorporated into our video test suite. Transition partners may not have the resources to annotate their data to the levels expected by DIVA systems. Additionally, they may want to use DIVA only to detect a single activity which presents subtle differences from the DIVA multi-class use case. And finally, operational environments may not have trained machine learning engineers on site. Any deployed DIVA system will require documentation and guidance developed for the appropriate audience in order to be successful. Our ultimate goal is shown here, in which core capabilities developed on DIVA are integrated into a partner's ecosystem of video sources, video data management, and other video analytics and analysis tools. Toward that end, our future work includes containerization, Technologies such as Docker would greatly reduce systems engineering friction for both testing and deployment. Continuing to improve operational trainability, for example, reducing the partner's annotation burden by fine-tuning the performer's models on partner data. Enhancing DIVE's data models to more accurately reflect the DIVA activity data models, and thus unlocking DIVE's potential as an annotation tool. And continuing to work with potential transition partners to develop their data sets to more accurately assess where DIVA capabilities will have the most impact. In conclusion, in this paper, we've described our experiences as we work to transition state-of-the-art video analytics systems from research to operations, an activity which tests assumptions at every level of both system and program design. Lessons we've learned for future R&D efforts include using containerization technology. While not a panacea, the standardization of system packages such approaches provide would minimize deployment issues and focus energy on API development. Related to containerization, providing implementations of common program I/O services would minimize time spent reinventing non-research related wheels and allow teams to focus on research. Research programs which use proxy data can encounter a data cliff, where assumptions inherent in the proxy data clash with the realities of operational data. DIVA turned this into a data slope, partly by using the surprise activity protocol, and partly through the use of the unknown facility data. The transition desire of increasing the scope of program data, of course, is in tension with the need to maintain a consistent baseline to monitor overall program progress. And finally, it's never too early to begin talking with potential transition partners and incorporating their use cases into the program. And finally, we'd like to say thank you to both the DIVA test and evaluation team and to the DIVA performers for their unstinting and generous support over the past 4 years. Thanks for watching.